Good evening and welcome back to Vegas October 1 Sounds. Tonight I'm going to talk more about supersonic projectiles and the sounds they hear. Now, for the last 4 months I've been drilling into people's head that when a rifle fires off a round, there's multiple sounds that it can produce. And the two dominant ones are, of course, the muzzle blast, which is the sound of the exploding gases leaving the barrel. And that's a one-time event for each round, and that propagates out in a spherical fashion across to wherever as far as it can. And then there's the sounds which are produced by the bullet, which out of a rifle, if it's traveling faster than the speed of sound, it's supersonic, and that supersonic projectile will break the sound barrier and produce a miniature boom. But it does so at every point along the projectile path as long as it remains supersonic. And it is that process which determines to a great extent what you hear from that and also as a function of your position relative to the bullet trajectory that also can modify what you hear. So let's draw some pictures and do some simple review just to set the stage, because what I'm going to talk about tonight is an extreme refinement upon the knowledge base for supersonic cracks. And why now, and why is it important? It's important because without this deep understanding of the nature and characteristics of the supersonic cracks, you could make bad assumptions and bad projections as to what you're hearing. And it's not the case that every recording location in the venue that evening would record both a supersonic crack and a supersonic projectile. And the reasons for that are many and varied, and we'll get into a couple of them this evening. But they could be as simple as, hey, you're hiding behind a truck, and since the supersonic projectile noises are a higher frequency and therefore pretty much line of sight unless they're reflected or refracted, then hiding behind something tends to block the sound. It could be as complex as the bullet stops somewhere, and then you have a whole host of questions asked that since the bullet hits something, it's no longer supersonic. Well, what becomes of the supersonic crack waves that were generated prior to when it stops, and when will I hear them? When won't I hear them? Also, the bullet could become non-supersonic just by the simple fact that it traveled too far and went below the speed of sound. But those are some of the things that could affect what you hear. But first, let's review a few of the basics of this. So, if we have a projectile, and I'm not going to draw, this in relationship to anything, it's just going to be a diagram. So it's a two-dimensional diagram of a three-dimensional process, and I'll try to explain it the best I can. So first, we're going to take the case of a bullet being fired from a gun and traveling kind of in a horizontal trajectory at a constant speed. And as that bullet travels, it generates these individual, collectively, whatever. It generates supersonic cracks all along its path. Bazillions of them. And as the bullet travels and it leaves these little cracks behind, they have time to propagate away from the bullet's trajectory. So at some point along this path, let's say, we just want to take a snapshot of what's happening. Well, by the time we get out here pretty far along, the sounds nearest the bullet have propagated very little distance away from its trajectory. But these back here at hundreds or thousands of feet away have had time to propagate out at the speed of sound quite a distance. And so they could end up being way out there. And similarly on the other side of the trajectory. And so drawing and connecting all those together, you get this line. And if we divide it as angles between the trajectory of the bullet and that line, then we have something known as the Mach angle. So alpha, in this case, equals the Mach angle, which would denote as m. And that basically is equal to the arc sine, or the inverse sine. Well, let's just write sine minus 1. Sine is a trigonometric function. The inverse sine of the ratio of the, well, it's 1 over m. So I shouldn't have put an equal there. 1 over m. So if we have if the bullet is traveling at Mach 1, then 1 over 1 is 1, and the arc sine of 1 is 90 degrees. So at that point in time, then, this angle would be, basically a flat line moving forward, like that. If, on the other hand, the bullet is traveling at Mach 3, then the ratio of the bullet speed, which I'll call VB, to the speed of sound, which I call C naught, equals, let's say, Mach 3, the bullet is traveling at 3 times the speed of sound. Whoa, you say, well, what's the speed of sound? Well, for that evening, C naught is about 1,100 feet per second. So if the bullet is to be traveling at Mach 3, then it has to be traveling at 3,300 feet per second, divided by 1,100 feet per second, equals m, which equals 3, which is the Mach number. So I should have scratched that out right there. M equals, in fact, let's just erase that and redraw it correctly here. M, which is the Mach number, is the ratio of the speed of the projectile divided by the speed of sound. So M equals VB over VC. And alpha, the angle there, is equal to the inverse sine. Now, don't start rolling your eyes just yet. This isn't that hard. 1 over m. So it's just a couple calculations there. And I'll go through several of them. So if we have a bullet traveling at 3,300 feet per second, and the speed of sound is 1,100 feet per second, then we end up with a Mach number of 3. And if we divide 1 over 3, or 0.333, and take the inverse sine, then we'll get the Mach angle. And I think I have a chart over here somewhere for that purposes. Yeah, here we go, 3. So for a Mach number of 3, 1 over m is 3, 1 over m is 0.33, and the angle would be 19.47. So for 19 degrees we have for a Mach 3. So Mach 3 would be, let's say, equals the alpha up here would be 19 degrees. And similarly, for Mach 2, if the bullet's traveling 2,200 feet per second, so if the bullet's traveling at 2,200 feet per second, and the speed of sound is 1,100, then that equals a Mach number of 2. So the bullet's traveling at Mach 2, and 1 over 2 is 0.5, and that would get, and the inverse sine of that, of 0.5, would give us from our table, 30 degrees. Okay, so for Mach 2, we have 30 degrees. Now, why is this relevant and important? And you can calculate that. They're fairly straightforward calculations. And how is that important? Because most bullets, as they travel out, don't stay at a constant velocity. So this Mach angle is constantly changing. And if we pull up a let's see, that would be this one, I think. Yeah. So in this case, we can see that and this comes from remembering for 0.223 rounds, called what the cartridge is. It's a 55 grain pointed soft tip, a pointed soft point. Then it is traveling, depending upon the distance, at the gun, about 3240 feet per second. At 100 yards, it's dropped to 2747, 200 yards, 23, 300 yards, 1900. And so we have to look at those yardages in terms of where the bullet's traveling to. So let's take a look at that. So what we have to first do is measure some yardages, and then we'll determine what the speed is for the distance traveled, and from that we can do the Mach angles and things like that. So let's erase this crud then. And go to a picture from Google Maps of the venue and everything. So go over to Google Maps. There we go. Then we can start measuring some things. So at one side of this little measuring stick, we got the Mandalay Bay, and we can measure, what it is to down here to the intersection of Mandalay Bay and the boulevard, which is about 741 feet. Okay, and then if we want to go to the sound booth, probably about 1,100 feet. And then if we want to go up here to the church, it's about 1,800 feet. Well, if we drop back over, so we had 700, 1,000, and 1,800. We drop over to our chart over here. We see that by the time 1,800 feet is more than 500 yards, so by the time the bullet has traveled that distance, it's dropped to 1,270, and it's a little bit further than that, so it's another 100 yards after that. It would probably have dropped below the speed of sound. So by the time the bullet reaches the church, it's no longer supersonic. And that's an important phenomenon, because at that point it's no longer generating supersonic cracks. I mean, all the ones that generated prior to that time are still floating through the air, but by the time it reaches the church, it probably is dropped. Now that's all assuming, a 223 round with a 55 grain slug and a various load. So for example, we had the 800 feet. So 800 feet is going to be not quite 300 yards, but a little more than that. So somewhere between 2,300 and 1,900 would be the distance. So if we were to just stick with 200 yards, i.e. 600 feet, then we're going to be at about Mach 2. Similarly, at 1,000 feet, we're going to have to calculate that one out, which would be 1905 / 1,100 is 1.7. And if we drop down into our chart here, I don't think I have one for 1.7. So it's going to be somewhere between 42 degrees and 30 degrees. So at each point, the Mach angle is different, and that affects when and how you'll hear the cracks. And so we have to take all that into account when we do any real calculations. Now, we're not ready to do real calculations yet, but I wanted to, give you an idea of where we're going to be headed. All right, so back to our example of what we want to cover. So for Mach 3, coming off the bullet, you have a fairly small angle, and by the time you reach the middle of the venue, you have a substantially larger Mach angle. And we have to be sure and draw things in proportion to those angles to have any real idea of what's happening with the sounds that's being produced by the supersonic projectile. All right, so the real point that I wanted to get to is this phenomena. We have a bullet. It's traveling. Well, let me cover a few other basics before we get to that part. We have a bullet. Go back to our model here like that. And it creates these supersonic cracks, and they collectively form a cone. And that cone has a Mach angle associated with it. And this is, kind of my representation of a 3D phenomena. Okay. Now, that cone, that the sounds at the front are being created at the speed of sound. Once the sounds leave the bullet, which is very, very quick, then they propagate at the speed of sound. And so the leading edge of that cone is, from this perspective anyway, and you can't tell from this whether I'm overhead, left, right, or center of it, but anyway, the leading edge of that cone continues to propagate out that way. Okay. And similarly on this side. So you see that it's propagating in a direction that's perpendicular to the leading edge of the cone. It's not the way the wavefront is. The bullet is going to the right, and it's creating these things in the direction of the bullet, but they're actually propagating away from the bullet at that angle, which is, as we discussed earlier, the Mach angle, alpha. So, how is this of importance? Well, if we ignore... I guess we should talk about one more thing before we go any further here. If we stick the ground in here, and let's just make it intercept that thing, so that the sound is eventually, even for horizontal to the ground, the cone of sound being generated is eventually going to hit the ground. And when it does, because it is a cone and it is hitting it at right angles to the ground, then the sound creates a pattern on the ground that's parabolic in nature. That is, the person here will hear the sound before the people do over there. Now, if, on the other hand, the cone, or the ground, actually, were more like this, and I know that's a bizarre scenario, but just think about it for a moment. If it were like that, then the pattern on that ground would be a circle. So the shape of the pattern of the times of arrivals of the supersonic crack on the ground are going to be somewhere from a parabola to a circle. And that will simply be based upon the angle of incident of that cone to the ground. And you're going, whoa, back up here. Why are we getting so complicated? We're getting so complicated because the shooter was at an elevated position, and therefore the supersonic cone was neither at right angles nor parallel to the ground. So, for example, if we have a bullet like that, and the ground is down here, okay, and then there's some angle there, and then the cone that's being created along there, and let's presuming it's going fast, and we've got a fairly narrow cone, like that. And as you can see, based upon how I drew it, the leading edge of that cone, the sonic cone, the cracks are almost parallel to the ground. And this can happen. And as the bullet slows down, the cone actually may become almost, that direction, in which case you'd get circles on the ground. So when you're shooting from an elevated position, the cone doesn't travel parallel to the ground, but it intercepts the ground. And in this case, the way I've drawn it, if those angles were all accurate, then everybody along the ground, provided that it remained at a constant velocity till it hit the ground, obviously, because obviously it's going to hit the ground somewhere. Right there. Then everybody down here on the ground would almost hear the crack at the same time. And that's kind of a strange concept, because we always imagine that the crack is traveling with the bullet, which is kind of true, that it is being produced by the bullet, but once it leaves the bullet, then it just does its normal thing and propagates at the speed of sound along the leading edge of the cone. And the orientation of that cone determines when people hear things. So in this case, everybody who's equidistant from the leading edge of the cone in the forward direction is going to hear it. Now you'll also observe that most of the top side of the cone is propagating out into space, so we're not really going to hear much there. So we're only going to be able to get one side of the cone, whereas if the cone was parallel to the ground, we'd be hearing both sides of potentially both sides, not the upward side, but the sides below the trajectory of the bullet. So in this case, where we stand matters. If we're standing here, having a drink, what are we going to hear? Who knows? And that's what we're going to discuss in a moment. What are we going to hear when this bullet strikes the ground there? And so from this angle, under these conditions, which are entirely possible, this is a little bit steep, but let's see. But if we were, anyway, let's presume this is correct. Then, when this bullet hits the ground, it no longer is producing supersonic cracks. By definition, it can't produce any sounds, actually. And if we were close, we'd probably hear the impact sound. Excuse me. If I could get my drawing instrument correct here, I'd be in good shape. Okay, there we are again. So, in this scenario, the cone would be generated all the way up until it impacts the ground, and therefore would be generating these sounds like that, all the way back to where the bullet origin, and can't draw it above there. So then everything inside that cone, all this in here, they'd be able to hear it, the original sonic crack, because it's prior to when the bullet made the impact. But those who are ahead of the bullet or more downstream from where the bullet impacted have a different scenario. For the people on the underneath side of this, they don't hear anything because it hits the ground and reflects directly back up for this arrangement. But these waves don't disappear. In fact, what they do, they continue, the waves at every moment, continue to propagate outwards. like that, but they don't generate anything new. In fact, if anything, they start to diminish, and they're sort of going off up into space. And on this end down here, if we draw a line, this meets them all up. You can see that in this case, the person, depending upon their position, will hear nothing, because the cracks don't make it to them because the bullet stopped. And similarly on the ground. Now what actually happens is that the last couple moments before the bullet impacted something produce a little bit of sound, and those little bit of sounds, kind of like the muzzle blast, propagate forward in this semi-spherical fashion, and because the ends of these lines bleed energy. Remember that sound is a pressure, and at the end of those lines, the blue lines heading up into the sky, it wants to bleed that energy off, but it's very, 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 very soft in nature, to the point where, unless you're extremely close, you're probably not going to hear any of them. So, for the green area here, nothing is heard, and the further you downstream you get from the bullet, the bigger the area. Now that's looking from a side perspective. So I kind of call this the Maxwell Smart cone of silence, and the shape of it is not the exact same as the conic shape of the supersonic cracks. It's something a little bit different, and I'll show you. I'll give you a better example in a moment. But the takeaway from this is that if we are shooting from an elevated position with a variable velocity projectile, which they all are, and that projectile is intercepted with the ground or the object, or actually even goes too far and loses its velocity, then the supersonic cracks are no longer generated, and hence ahead of the bullet in some fashion there's this area where the supersonic cracks are neither going to be heard nor recorded, unless you have extremely sensitive equipment and there's no background noise. So it's not the case that every position always records a supersonic crack and a muzzle if the bullets don't fly past you. And as we well know, in Vegas that evening, a lot of bullets hit the ground. A lot of places on the ground are people. So we should see this phenomena quite often if we are directly downstream from the bullet. Well, you say, well, how big is this area? Well, this is a side view, and this really shows that most of the radiation from the supersonic crack in this scenario goes up into the sky, and unless it hits something and reflects back down, there's not much you're going to hear. But everybody back behind the impact point in this cone will intercept the supersonic crack, and they'll hear it very loud with the little bit of noise that comes up. In fact, the impact noise is probably stronger than the few supersonic cracks that were generated there and propagate forward. So let's draw this thing from an overhead view so we can get a much better idea from an overhead view onto the ground what this might look like. All right. So once again, let's kind of draw an outline of the venue here. So if the venue's kind of like this, and here's the boulevard going in this direction, and here's Mandalay Bay Road, and then over here we have Mandalay Bay itself. And I know that's not exactly accurate because, well, let's make it a little bit more accurate. Mandalay Bay should be down a little bit. Should be more like this. Okay. In that scenario, when we fire a bullet, the average bullet is probably going to go this direction. Alright. And we previously said this is about 700 feet. That's a shitty 7. This is about 1,000 feet. And over here is greater than 1,500 feet. At which point the bullet's starting to become pretty slow compared to the speed of sound. Alright. So the Mach angle is not going to remain constant. But let's start simple. And let's say that we have a fairly narrow Mach angle, fairly fast bullet over here. Okay. And let's say that it hits something right there on the street or on cop corner, and it hits one of those vans. Then the supersonic crack production stops, and so the only sound that we can hear outside of the cone behind it would be the sounds that now and the easiest way for me to do this is draw a right angle to that thing, and I'm going to do that just so I can make a good graph. Like that. Alright, so that supersonic cracks that were generated, and you notice they start over there by the Mandalay Bay. They don't go on forever now. So the portion on the north side of the trajectory of the bullet is taking this path, and the one on the south side is taking the following path. Alright, well, what does that mean? That means that for that bullet which hit near the cops, and let's go on until it just eventually dies out. Would not be heard for this entire region. Whoa, you say. How could that be? Well, that's just the nature of the beast. Because when the bullet hits something downstream, there's no way for the sound to be generated. Now, it's not exactly like that, but it's close enough. And this is, this is a two-dimensional representation of a three-dimensional process. And as I showed you, when you look at it from the side, things are actually going up into the air also. So the takeaway from this is that when you have a recorder anywhere in the venue, or even way over here, then and the bullet hit the cop cars on the corner, you're probably not going to hear the sonic crack unless you're in the blue zone. That sink in? Okay. Well, let's try it for a different position. Let's say now that the bullet made it all the way out to the middle of the venue, which at 1,000 feet, what did we say? I think we said that it was going to be traveling. I have to go back and look because I need to determine the Mach angle now. For 1,000 feet, 300 yards, Mach, or it's going to be traveling 1,900 feet a second, which I said was 1900/1100 for speed of sound. 1.72, and from my chart I figured that that would be somewhere between, let's just call it 35 degrees. So the Mach angle is going to be 35 degrees. So In this case, if the bullet strikes somewhere in the middle of the venue, there, then we're going to have a Mach angle of 35 degrees. And let's see if I can faithfully reproduce 35 degrees. I think that that's probably about 35 degrees. Yeah, that's probably about 35 degrees, not quite 45. Okay, so oh, it's not very symmetrical though, is it? No. Okay. Gotta try to kind of be a little bit reliable here. I think that's better. Yeah. Okay. So there we have the sonic cone in a 2D representation, and now let's draw in the right angles to those lines. And then let's fill it in for all the places that would hear the supersonic crack. And you can see why I drew the right angles to it. Okay, so everybody in the blue is going to hear and record a supersonic crack. So now we got a much larger area. But you'll notice that there are several places that don't. And specifically, the church, Budweiser tent, and Chicken Shack. Maybe even some things above, what was that, gate 5, wasn't it? I think gate 5, and the hospital tent. And probably almost down to gate 6. Where was, I don't know, somewhere in here. So gate 6 is kind of close. That little cop car where Dan Blazarian was hiding behind there would. Anybody along the boulevard would. Anybody along Mandalay Bay Road, and when it turned into Giles until it reached this point, would. The people escaping to the airport probably would not. People at Hooters, no. People at MGM, I mean Tropicana, would. People at MGM would. Luxor, oh yeah. Anything along there, Luxor or the Excalibur, or anybody along the boulevard would. But not the people on the east side of the venue past the sound booth in this angle here. And you can see that based upon the Mach angle, the shape of the zone of silence or cone of silence ahead changes also. So you have a scenario here where when somebody comes along and says that they hear sounds over here that are supersonic cracks, you have a couple questions to answer. Where was the path of the bullet and where did it hit? Because to get a supersonic crack over here, the bullet has to be further out or at a different angle. Now, let's take this same bullet, or a different bullet, and change its path. So now I've got to erase a bunch of stuff here. Okay. I don't want to kind of do it without erasing all my other things. Don't want that. I don't want that. That. Oh well. Okay, I wanted that one. No, I don't, because I want to change it. Let's say instead of going to the sound booth, the bullet was fired over here towards the stage and hit somewhere near the stage. Poof. I know the stage is a little further in, and it's going to be a little bit shorter, so the Mach angle is going to be a little bit bigger. So in this case, let's say 40 degrees. 40 degrees coming that way. 40 degrees coming this way. Almost a right angle. Okay, and then we draw the right angles to that. And now you can see that the cone of silence is in a different location, because everybody now in the blue and back here, of course, in the original crack, is going to receive a crack for that, and it's going to go on and 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 on out there. Same down here. So you can see how even changing the angle of the trajectory, in this case by about 20 degrees, substantially altered who does and does not receive the supersonic crack. And over here in the green are those who don't. Now, for bullets which hit further over here in this area, then obviously this cone is going to get the Mach angle is going to get larger, and there'll be more and more people. This cone of silence shrinks, and there'll be more and more people. So when you hear something, you have to know the trajectory of the bullet before you can make a real assertion as to what it is or is not. So let's take a real example. And it's going to be one that I do pretty extensive analysis on. But to eliminate that, we have, because we're going to kind of want to work backwards here. All right. Let's take the church. There is a video in which we deal with volley 7, located somewhere in the church vicinity, not at the church, right here. And volley 7 comes along, and for the most part it's just got the muzzle blast. But then towards the end it's got this very prominent thing which sounds like a supersonic crack. Okay, so we have a scenario where for volley 7 we obviously have bullets going somewhere, and it was recorded out at here. So we have to ask ourselves, why don't we hear the supersonic cracks? Again, there could be multiple reasons why we don't, and then why do we hear this one? And so first you have to determine, was the recording hiding behind something? In this case, no, it has line of sight to the Mandalay Bay. There are things in between, but you can see the 32nd floor. Okay? But that only determines whether or not you can hear the muzzle blast, and obviously we could, because every single muzzle blast for every single round was recorded. So, the question becomes, why don't we hear any supersonic cracks for that and this, but we do for those? And actually there are a couple more in there, but this is the primary one we want to talk about. Well, one possible explanation is that the bullet went astray. Pardon me a moment, I need to take a drink. That is, the bullet took a trajectory such that we could hear the supersonic crack, which, since we have a volley going on right all the time, that would be the most probable scenario, and we do have a couple of others. But why is it so loud, and why are these so dim, and why are the muzzle blasts so loud? Muzzle blasts are loud because we have a direct line of sight. That's just plain and simple stuff. Why are these over here so weak? Well, that's when you have to start looking at videos to determine the trajectory path. And regardless of whether you want to call this a sniper round or a part of volley 7 or any other thing, without knowing the trajectory path, you can basically make no statements about where the shooter was. So you start looking at videos, and there's 50 or more that record volley 7. And so you start looking. And so let's pick a different color. Let's go with let's go with a dark blue. Well, the first thing you do is start looking in the immediate vicinity. And so you pull up videos here and here and a couple over there, and you notice that you know, kind of pretty much the same scenario as where you're at, is that there's not too many supersonic cracks. You say, okay, I would have expected more there, but that's okay. So then you pull up something down here, and you have the supersonic crack recorded. So let's draw that in a yellowish. Blues are no supersonic cracks. And then you pull up one over here. You got it, cracks. Here you got 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 cracks. Over here you got cracks, and over here you got cracks. Okay, so you start to see a pattern here, don't you? So now the question is, where is the path of the bullet coming from? Well, you have to make a little analysis, and you have to view all the 50 videos to get a really good idea, but you ultimately find out that the quote-unquote loudest sounds, or the most muzzles, were recorded in this area and in this area along these paths. And the greatest intensities were in this little zone. So since the intensity here is much larger than the intensity up here, you kind of have to say that the source of the shooter was up here, namely towards Mandalay Bay, and that the bullet had to have made it at least as far as you, or the bullet could have gone this direction. Because if the bullet goes from Mandalay Bay out towards the field, then you'll recall that the field of the cracks was in that direction. All right. Now, for that scenario, the bullet could have landed as far back as probably the middle of the venue. Although in this case, that's not quite true, because I said there were no cracks up there, didn't I? So we have to have something that looks more like this. Oops, didn't want to do that. More like this, though. And so you can get a general idea that the bullet could actually have hit further back here, and you would have still not heard it up there. Most of the bullets, excuse me, I just did that backward, and I just did a big screw up. We heard the one, so the original plan was right, that you have to have blue that goes over there. So the bullet had to have either stopped there or continued on, but was probably either in the direction of the field or the direction up there. Either way, I haven't quite figured it out yet, but I'm going to, and I'm going to display all the things. So what I'm demonstrating here is that it gets extremely complex to say from one sound what's going on, and that the cracks do these weird things. And once again, this is a greater complexity than I've explained to date. because normally I pick locations which are down here at Oasis or Luxor or all that, which have great big angles to the trajectory of the bullet. That is, they're far away from the bullet path, and because they are, they're in these blue ones, and they record both the supersonic crack and the projectile, regardless of where the bullet strikes. Let me go over that again. So for and I'll get to it. I'm just erasing this cred here. Alright, let's get back to drawing. So for the Mandalay Bay here, and a projectile coming out from the north side going northeast, excuse me, then a recording location over here at Oasis Apartments, or up here at Luxor, or anywhere along the boulevard here, is going to, for the Oasis part, we're going to hear the supersonic cracks that are generated here. For the Luxor, probably about the same thing, maybe there. For the boulevard, we're going to hear them probably like that. This is where they're generated. So if the bullet stops anywhere past these points, then it wouldn't matter, because you'd still hear them. And that's another way of looking at the whole scenario. And that's where I generally select things, is along these paths on the outer fringes, that will give me a good representation of what everything is without having to deal with the chaos generated by being downstream from a bullet which hits something. And the time when I normally look at those over in that direction is when I want to determine where a bullet hits. So you just have to remember that when you're dealing with recording locations that are directly downstream from potential bullets, that it's not the case that directly downstream will hear loud sounds if the bullet doesn't make it to your location. Now, if the bullet makes it to your location, then yeah, those cracks are going to be in your face, knocking you down onto the ground. But if they hit, even as much as 100 or 200 feet earlier, then it's less likely that you'll hear those supersonic cracks by the phenomena that I just explained as the cone of silence. And it is a cone in most regards. It's not the same size and shape as the one created by the bullet where you do hear them, but it is a cone. So I think that gives a basic handle on a phenomena that I'm going to be talking about a lot more. And it gives people an idea that even for one bullet, there's a lot of calculations going on. Now, imagine that each bullet is taking a separate path, even if it's ever so slight. These things are all over the place, and you can see where you'd have the supersonic cracks over in the venue on the east side of the venue area being kind of sporadic, and the more northeast you go, the more sporadic they become, until a lot of the recordings out in that region don't record too much at all. But it's all a function of the bullet path. And for volley 7 in particular, we know that from a previous analysis is that the volley went probably as far north as gate 2B and probably as far south as the stage area. So those bullets were all over the place. Now, and so for the bullets that went down towards the stage, they'd be recorded up there. For the bullets that went more northerly, shall we say, they wouldn't be recorded as much at the church, but certainly along the boulevard and everywhere they would be. Alright, there was a couple other things. Oh yeah. Now I haven't told you the complete story here, because for that shot, which is about the 6th or 7th shot from the end of volley 7, there is something else going on, and I haven't quite figured it out yet I still believe that the shot came from the Mandalay Bay, but there's something unique about that shot, and it's either got a higher load or a cooked off shot or a different type of round or a tracer round or something, because its energy signature is far greater than the signature of the rounds that were fired in close proximity to it. And I went into that investigation thinking about the claim that there was a sniper round being fired over there. And what I ended up was back at Mandalay Bay, of course, and I can see even at Mandalay Bay from the spectrograms that there's something unique and different about that round. Now, I don't believe it was fired from a different gun, because when you record these things, that the places that record every single muzzle shot and every single supersonic crack, they all come up with the same count. So unless you want to say that another gun was there that was matching the timing perfectly, it was the same. It was only one gun, not two guns. So, and even then, if you had another gun, you'd have to. Well, anyway, let's just forget that argument. And so I'll be doing probably about 3 videos, because it was a fairly lengthy investigation into what I found and how I came up with the analysis. But you can see how, for me anyway, it gets really frustrating when somebody comes up with one little supersonic crack, and I know to nail down what that supersonic crack is takes a tremendous amount of work. And I just, as I said many times, I just kind of cringe when people hear one sound that looks a little different in a particular area and claim, oh yeah, we've got a second gun or a sniper or talking guns or all that. Supersonic cracks do weird, strange things. And without a lot of knowledge and a lot of calculations, you can't just say right off the top of your head what it is. Even by listening to 100 of them in one video, you still can't say what it is. Because I'll show you these spectrograms where over on this boulevard, we've got up to 5 or 6 loud sounds produced by one bullet. And it's because of the nature of the reflections and the close proximity to the source of the gun. And much like in the Corey Langdon video, when you listen to that thing, man, you'd swear that there were 3 guns going off by the loudness of some of those things, but they aren't. They're echoes. Okay, well, I've probably gone off long enough and made things a little bit more muddy, but I just wanted to get across that so far we haven't talked about the nitty-gritty extreme complexities of some of these sounds, and we haven't even gotten into the effects of the buildings and walls and bushes and elevations, which for the supersonic crack can also have another very big impact on whether you hear the sounds or not. Being the VIP booths, the Coca-Cola booths, if you're on the backside of those, you're not going to hear too many supersonic cracks unless the bullets made it over or by them, because the supersonic cracks are pretty directional and they get blocked by objects that large. Whereas the muzzle sounds, they'll kind of bend around those buildings and you'll still hear some stuff. And so the supersonic cracks really are a different complex beast that's your worst nightmares in terms of coming up with realistic assessments where they come from and what the true nature of them is. So people can claim anything they want, but if you haven't taken at least 10 or 12 hours to determine and verify what that one sound is, then it's just not a credible statement, at least ways in my eyes. So anyway, that's the rant, that's the bitch. I hope I gave a deeper understanding. It's a little quick. I'll give more examples as I go through the analysis of that one video. And that type of analysis will apply to multiple videos, because all the time I have people asking me that same question. Hey, what's this sound here that looks different than the others? That's maybe a sniper shot or something like that. But almost invariably, they end up being artifacts of echoes, reflections, or artifacts of the way the bullet went and the physics of the supersonic crack generation. And that's Richard out for the evening.